All right, so this is going to be a video that's an extension from the last one. So if you did not see that last one, make sure you do watch that. And it's basically the zeros of polynomials. And that's also an extension of the video before that involving quadratic equations and finding the zeros of that. It's very similar to find the zeros of polynomials. First thing is we're going to apply the fundamental theorem of algebra. So first we're going to learn what that actually is. Next, we're going to use common tests to determine the nature of polynomials as zeros. And then we're going to factor a polynomial with real coefficients into a product of linear factors and irreducible quadratic factors. And then we're eventually going to find those zeros from that. So first thing we're going to go over what's called rational zeros theorem or rational roots theorem. Basically what rational roots theorem helps you do is figure out if there are any rational roots or rational zeros. And to do that, basically what you're going to need to do is figure out what p divided by q is. P is going to be the factor that's with the a sub 0. And the q is the factor that's going to be with the a sub n. So the number that's before that, it's going to be all the factors divided by each other. It's going to make more sense when we actually do an example, but p over q is where you're going to want to start. It's all the possible rational zeros that you can use, and then you're going to use a graphing calculator or just the graph itself to figure out, what the other factors are just from that. And then it's just a huge process of using synthetic division or long division to figure out the rest of the zeros. So let's actually try to do some examples to kind of solidify this a little bit more, because that explanation was definitely not good enough. So first thing that we're going to do is it says list all possible rational zeros. What we're going to do is we're going to do p divided by q. And p is all the factors of whatever this last term is. So in this case, it's going to be -3. So then all the factors of -3 could be like 1 times -3 or -1 times 3. So hopefully you notice it's just going to be plus or minus all of those values there. So it's going to be plus or minus 1 and plus or minus 3 for that top part, that p value basically. The q, we're going to do the similar kind of thing, only this time it's 2. So that's going to be 1 times 2 or -1 times -2. So hopefully you realize it's always just going to be plus or minus whatever the factors are going to be. So in this case, 1 and 2. So now our possible rational zeros are going to be all of those possible values divided by each other. So it's going to be plus or minus 1 over 1, plus or minus 3 over 1. So I basically did this divided by this, and then 3 divided by this. And then we're going to do the same thing with the 2. So it's also going to be plus or minus 1 divided by 2, and plus or minus 3 divided by 2. So that's basically the final answer for these, is all of that. Obviously, you have to simplify those because you're not going to write 3 over 1 or 1 over 1. So it's just going to be plus or minus 1, plus or minus 3, plus or minus 1/2, and plus or minus 3/2. And that's going to be the final answer for that one. So again, you just find all the factors of that last term, the -3, and all the factors of the first term too, and divide those. Those are all the possible rational zeros that you can have. So what you're going to essentially do with this, the next problem actually, is figure out if any of those actually work. You're going to plug in 1, you're going to plug in 3, you're going to plug in -1, you're going to plug in -3, positive 1/2, -1/2, positive 3/2, -3/2, and figure out, do any of them actually give you a 0? And if they do give you a 0, then you can use that to basically complete the factorization of f. That's what we're going to do in this next problem right here. So it says find all the zeros. We found all the possible zeros, but not all of those are going to work. So that's what we're going to figure out right now. So first thing I'm going to do is figure out, I'm going to write all the possible x values in, and then I'm going to plug them into the f of x equation. I would use a calculator on this just because it just goes really fast if you do that. So we're going to do 1, -1, 3, -3, 1/2, -1/2, 3/2, and -3/2. And we're going to plug those all into the f of x function and get values. So I'm going to do that really quick on the calculator. So if you do that, you're going to get 0, 4, 84, 0, -7/2, 0, 9, and 15 over 2. So from there, it says find all the zeros. The zeros would be x equals 1, x equals -3, and x equals -1/2. Now, if you notice, if we didn't use rational roots theorem on this, we would not have even known where to start on this. I guess you could have looked at the graph and find the intersections as well, but it helps us find those values. Another thing that we're going to talk about in just a second is there should be 3 answers because of that highest power being a 3. So whatever the highest power is, whatever the degree of the polynomial is, that's how many answers you should have, including multiplicities. So we have 3 answers, so that is all the answers for this. Now then it says, the next part right here, it says complete the factorization of f. So we're going to factor f. And this is going to relate back to the last video that we talked about this kind of thing. So f of x is going to be equal to x minus 1 times x minus -3, which is just x plus 3, and then x minus -1/2, which is just x plus 1/2. Now, there is a leading term of a 2 here, so we also have to put a 2 in front of this. But if you notice, it's just going to be x minus the roots, or x minus the zeros, essentially, to figure out each of these. Okay, so that is the complete factorization right there of f of x. If you expanded out that f of x factored equation that I have right there, you're going to actually get the original 2x cubed plus 5x squared minus 4x minus 3. So the zeros actually help us find the factors because of factor theorem, which again was discussed in the last video. One thing you could have also done, because this has a fraction here, is you could have distributed the 2 there. So you could have had x minus 1 times x plus 3, and then distribute the 2 to this thing right here, and you would get 2x plus 1. So now if you notice, all of them do not have any fractions in them. You could do that if you want, you don't really have to. Okay, the next thing, intermediate value theorem. If f is a polynomial and a and b are 2 real numbers for which f of a and f of b have opposite signs, then f has at least one real zero between them. So what intermediate value theorem basically states is there's a value in the middle. Intermediate means in the middle, value means value. So the theorem is there's a value in the middle if it's continuous, and a polynomial is continuous. So all you have to do is prove that there's a negative value and a positive value, and then somewhere in between, it has to hit 0. And that's what it's essentially saying. So as an example, I'm just going to graph an example really quick just to kind of make this make a little bit more sense. So I'm going to have some polynomial. Let's just do something like this. Doesn't really matter. Okay, if you have a negative value, let's just say this is a right here, and let's just say this is b over here. If you notice, this a value is going to be negative, and this b value right here is going to be positive. Since it's a polynomial, somewhere in between it has to hit 0, because f of a is negative and f of b is positive. That means it had to have crossed 0 at least once. Now this one has 3 times because that's what I drew, but that's the main thing, is there's at least one 0 between that a and the b. There has to be if one's positive and one's negative. It's kind of a common sense theorem. I don't know, it's something you're going to cover again in calculus, but it's good to kind of introduce it now so it makes a little bit more sense when you do see it again, if you do see it again. All right, this one right here, show that f of x is equal to x cubed plus 3x minus 1 has at least one 0 between 1 and 2. So what we're going to do is we're going to plug in 1, and you're going to get 1 plus 3 minus 7, and so that's going to be negative 3. And then we're going to do f of 2, and that's going to be 8 plus 6 minus 7, which is going to be equal to 7. So if you notice, it went from negative 3 to 7, so there at least has to be one 0 in between because one's negative and one's positive. I basically showed it by doing that right there, and that basically proves it that there has to be at least one 0 in between. It has to hit that middle value. It doesn't just skip over it. Next thing we're going to talk about is the fundamental theorem of algebra. I kind of talked about this just a second ago, but basically if a polynomial p has a degree n, and n is greater than or equal to 1, then p has at least one 0. In fact, even more so than that, a polynomial of degree n has exactly n zeros counting multiplicities. So that's actually what we're going to be using primarily with this fundamental theorem of algebra. Whatever the degree is, whatever the highest power is for that polynomial, that's how many answers there are. So many zeros there are, how many roots there are. Okay, next we're going to talk about conjugate roots theorem. Basically what this means is that anytime you have a conjugate, this basically means anytime you have a complex root, you're always going to have its conjugate as well. So basically what this theorem states is if you had some root that was a plus bi, you automatically have another root that's a minus bi. It has to follow that. So for example, say you worked out some problem and it ended up being as 3 plus 2i is one of your answers, then automatically 3 minus 2i has to be another answer. No matter what, you cannot break this theorem. It is literally impossible. So we're actually going to use this when solving the problems. If it ends up where they give you one complex number, you automatically know that its complex conjugate also has to be an answer. So let's look at an example where we have to use this fundamental theorem of algebra. All right, so it says construct a 4th degree polynomial whose real coefficients who have these things as zeros. Okay, right away, you know it's going to be x minus 2 because it's x minus a root, x minus negative 5, x minus 1 plus I, but since this is a complex number that has an imaginary part to it, you automatically have to do its conjugate as well. So that means 1 minus I has to also be another one of the roots. So I'm going to do something like that. So here's where that new one comes into play. So they only give you one. You have to know that they always come in pairs, the conjugate pairs. So you also have that other one there, whose graph passes through 1, 12. That means we don't know what this a value is in the front, and this is the function that we're going to be trying to figure out right here. Okay, so I did x minus the roots for all of them. I'm going to simplify this stuff a little bit here, like this and this, this and this, and this becomes a minus, this and this, and that becomes a plus. Okay, so we have something like that. All right, so let's simplify this out a little bit and then try to figure out what that a value is. By the way, you're always going to figure out the a value from whatever's the points that's given there. So just make sure you're aware of that. X minus 2 times x plus 5 times x minus 1 minus I times x minus 1 plus I. So we have something like that. Now we're going to try to figure out this a value. All we have to do is plug in 1, and you should get 12. So that means it's going to be a times 1 minus 2 times 1 plus 5. If you notice, I'm just putting 1 in for all the x's. Super simple. So you end up something like that. Okay, that's going to be negative 1. That's going to be 6. That cancels, so it's negative I. That cancels, so it's just positive I. And you end up with 12 is equal to a times negative 6 times negative I times I. Well, I times I, if you remember, is negative 1. So this is going to be a negative negative 1, which is just positive 1. And you're going to be left with a times negative 6 is equal to 12. So for this problem, a is going to be equal to negative 2. So your final answer should be, we're not going to try to expand this out because it would take a year. It would just be negative 2 times x minus 2 times x plus 5 times x minus 1 minus I times x minus 1 plus I. And that is the final answer, believe it or not. If you wanted to expand that out, you absolutely can, but it would just take a long time and it's just really not worth it. So we're just going to leave it like that. All right, last but not least, factoring polynomials. So it's similar to what we were just talking about a second ago. There's a bunch of steps that you can follow here, like start by factoring as much as you possibly can, so it's easy as possible. Use quadratic formula if applicable, so we might run into a thing where we have to use quadratic formula. We're going to use rational zeros theorem. We're going to test the possible zeros, just like with our calculator like we did before, to try to break down or deflate that polynomial as much as possible. And then we're going to repeat that until we get to a quadratic or a linear polynomial, and then we have all of our factors and we should be good to go. Now that's a lot of steps. The easiest way to do that is just to go through a problem like we've kind of been saying for all these other problems. So that's the first thing that we're going to do, is we're going to try to figure out what this breaks down to. Okay, first thing we're going to use is rational roots theorem to figure out all the possible roots that we can do. Okay, the possible roots, that's where you have to do the p over q thing. So we're going to do p over q, which is going to be equal to, I'm just going to put the plus or minus in front right away, and I'm going to write all the possible values down in here. All right, so we obviously have 1 in 625 because we're just looking for all the factors of 625. But there's obviously going to be a lot of those because it's a huge number. So we also have 5 in 125. We have 25 and 25. So that means we actually kind of hit the dead end there because those are the only possible values. After that, we're just going to be repeating the 125 and 5 and all that other stuff. Then we're going to be dividing it by the q. In this case, the value is 1. So we end up having something like that. So all the possible values, the possible roots would be plus or minus 1, 625, 5, 125, and 25. So from here, we're going to use our calculator and try to test all of those values and figure out which of them actually give me a 0. So I'm going to plug this whole thing in my calculator. It's going to take a little bit, but the calculator is doing most of the work. So plugging those all in my calculator, the only ones that actually work are going to be x equals plus or minus 5. So negative 5 and positive 5 work as roots for this. So that means if it's plus or minus 5, then the roots are going to be x minus 5 and x plus 5. So those are two of the factors right away. So what we're going to do is we're going to use synthetic division on this to break down that polynomial so we can get all the other factors as well. So right now, this f of x is actually equal to x minus 5, x plus 5, and then we're still missing 2 other factors because technically there should be 4 factors because of the 4 there. If you remember from fundamental theorem of algebra, there should be 4 total factors. So we have 2 of them. We're halfway done. Now what we need to do is break down this polynomial as much as possible using synthetic division. So we have 1, negative 8, there's no x squared, so it's a 0, 200, and negative 625. We're going to drop this down, put the 1 there, multiplies 5, add down, multiply again, negative 15, add down, multiply again, you get negative 75, add down, multiply there, you get 625, 0, which you should get a 0 on this because technically it's a factor, there should be no remainder. So that's with the 5. That's dividing out x minus 5. Now we're going to divide out x plus 5. So that means on the outside here, I'm just going to continue on with this. I'm going to put a negative 5, and we're just repeating the process. Drop this down, it's a 1. Put this here as a negative 5, negative 8, 40, 25, negative 125, 0. So now we're left with a quadratic. When we divided out one of the x minus 5s, you end up with an x to the third for the degree. Now we have an x squared. So this whole thing right here basically becomes, I'm going to do this over here, it basically becomes x squared minus 8x plus 25 is equal to 0. Okay, the remainder is 0. We have to set this equal to 0 to find all of the zeros. Once we find the zeros, we can basically find all of the factors. Now for this one, it's quadratic. So what we're going to do is we are going to simplify it or solve it using quadratic formula. So that's what we're going to do right now. So it's going to be x is equal to negative b, which is just going to be 8, plus or minus the square root of b squared minus 4ac, which is just 100. So it looks like we're going to have an imaginary number here because we're doing the square root of a negative. And divide that by 2. All right, from here we're going to simplify this out. So it's going to be 8 plus or minus the square root of negative 36 divided by 2. Okay, I'm going to pull the I out of there. So I'm going to make this positive, pull the I out. And then from here, simplify it. So it's going to be 8 plus or minus 6i divided by 2. Okay, I'm going to divide everything on the top by 2 and everything on the bottom by 2. So then you end up with 4 plus or minus 3i divided by 1. So x is equal to 4 plus or minus 3i. Now this 4 plus or minus 3i, that's technically two x's, two zeros, because it's x plus 3i and x minus 4i. So now we actually figured out all 4 of the zeros, which means we figured out all 4 of the factors. So we're going to fill in these two blanks right here with those factors. So now it's going to be times x minus 4 plus 3i and x minus 4 minus 3i. And that is the final answer. That is the complete factoring of that original polynomial. If you notice, there's 4 factors, and there should be because that highest power is 4. So you are going to want to study this problem because it's very, very, very technique-based, and you kind of have to memorize the steps to doing this, okay? So first thing I did, I used rational roots theorem. That's what this part is right here. I used rational roots theorem to find all the possible roots that we could use. That's basically what this part is right here, finding all the possible roots. Then I used a calculator to figure out which of them actually worked. The only ones that worked were negative and positive 5. So that means that x minus 5 is one of the factors and x plus 5 is one of the factors. From there, I used synthetic division on the 5 and the negative 5 to get a quadratic equation right there. From that quadratic equation, I set it equal to 0 and solved to find the roots. Tried to solve to find the zeros. The zeros and roots mean the same thing. And once I found those zeros, I put them in factored form right up here in red. And you can see the full answer there with all the factors. And that's basically how you do that problem. Lots of steps, lots to really break down. Make sure you take good notes on this and study it vividly because you're going to need this for the next test. So that's a video on the zeros of polynomials. We went over fundamental theorem of algebra, which remember, it states whatever the degree is of that polynomial, that's how many possible roots or possible factors there's going to be, including multiplicity. You got to make sure you include that as well. Using common tests to determine the nature of polynomial zeros, and we factored a polynomial with real coefficients into a product of linear factors and quadratic factors as well. If you have any questions about anything in this video, let me know.